So let's start with that. Okay. To go through and balance it, we would check the elements on each side, okay, changing the coefficients out, which should come out with 2, 6, 2, and 3. Hopefully everybody's got that. Okay. And I am really just trusting Brandon to be right. And since everybody else seems to agree with him, we'll run with that. Okay. The next part is focusing on what are we trying to get to? Well, what do I want to know? The liters of hydrogen. So I have a big old question mark for the liters of hydrogen. I don't know why I wrote it that way again. Question mark, liters. What information am I given? I'm given 0.165 grams of the aluminum metal. Am I given anything else? No. Okay. So if that's all I've got, what I now want to do is move to my equation format that we've been working with. I want liters of hydrogen, so liters of H2, as my final answer. And I want to write down what I'm starting with. Okay. 0.165 grams of aluminum. That 0.165 grams of aluminum could be a little bit tricky to manipulate and work with. Okay, why? Where can I take grams of aluminum to as a unit? I could go to moles. I could go to kilograms. I could go to hectograms. All of those are of aluminum. Is that what I want here? Grams or aluminum? It's not grams. It's not aluminum. So what I would argue that we should start with is focus on that unit and trying to convert the liters of hydrogen to something else. Okay. Do we have a conversion factor that allows us to convert the liters of hydrogen to something else? We only, okay, I didn't think of that one. We have milliliters. We could go to milliliters of hydrogen. That is a possible conversion. Okay. Does that help get me to grams? Is milliliters a measure of mass? No. We can talk about that relationship later. Is hydrogen the same as aluminum? No. So while doing the milliliter conversion is something I could theoretically do, that doesn't get me closer. Is there another conversion, say that we talked about 2 slides ago? Not even 2 slides ago, 1 slide ago. Yes. What was that conversion? 22.4 liters is equal to 1 mole. So I could set up a conversion factor where liters of H2 needs to be on top. Why does it need to be on top?
Because that's what our final answer.
It's where it needs to show up in my final answer. And what should show up on the bottom? Moles of hydrogen. What are the numbers associated with that conversion factor? 22.4 liters is 1 mole. So this does bring in the liter unit, but this makes things complicated because I now have moles of hydrogen. I don't want moles of hydrogen. So what do I know has to happen? I need to cancel the moles of hydrogen with something. Okay? Yeah, we are reverse engineering this. Moles of hydrogen. Am I given moles of hydrogen in the question? Since people might be referencing this one, let's get rid of that one. Am I given moles of hydrogen in the equation? Question.
Yes.
Not in the question, but I could introduce the moles of hydrogen coming from the balanced equation. That 3 in front of the H2 in my balanced equation is 3 moles of hydrogen. Okay? But is that how much I actually have in this reaction? That's what's produced if what? I mix 2 moles of aluminum and 6 moles of HCl. Am I mixing 2 moles of aluminum? 0.0165 grams of aluminum. What is 1 mole of aluminum? 26.98 grams is 1 mole. Am I starting with 1 mole or 2 moles of aluminum? No. So that 3 moles is only produced when 2 moles of aluminum are reacted. That's what the equation tells me. Okay? So really, I've got a conversion factor. I can relate the moles of hydrogen to the moles of aluminum. Okay? Could I relate the moles of hydrogen to, say, the moles of HCl? Yeah. Which conversion factor do I want to use? Why aluminum? I'm given something about the aluminum. That's why I want to pick and convert with my aluminum. What numbers show up in front of those? Where does the 3 show up? Way to start with me yelling at you and then end by fixing your mistake at the same time. 3 belongs with the moles of hydrogen because that's what our equation shows. The 3 is in front of the hydrogen. So I should have 3 moles of hydrogen, 2 moles of aluminum. The unit I now have is liters of hydrogen, but I still have this moles of aluminum. Do I want moles of aluminum in my answer?
No.
So what has to happen? I need to get rid of that unit. Am I given the moles of aluminum?
Well, yes, because you said.
Where does it say in that question, moles of aluminum? No, it does not. Which means I need a conversion. Okay. I need a conversion factor that involves the moles of aluminum. What conversion factor do I want to use? Why grams? I am given the grams of aluminum in the question. What is the conversion factor between the moles of aluminum and the grams of aluminum? 1 mole is 26.98 grams. That information was found on the periodic table. Where was the 0.165 grams of aluminum found? It was in the question. Where's the 3/2 found? Our balanced equation. Where was the 22.4 liters is 1 mole? Okay, we're going to run into a couple of different ways to answer that. We could say textbook. I'm not positive, but I think it's on the front of the exam. And because you are expected to be working with and using it, you might also memorize it so that you don't have to look it up. Yes?
So where you put the 3 moles of H2 over 2 moles of aluminum.
Yes.
And then on the other one you said we didn't know what the mole of aluminum was. Why did you put 2 on the bottom and then 1 on top? Because you didn't know what it was.
So it sounds like you're asking about this. Okay. I don't know what the moles of aluminum are. So what I need to do is come up with a conversion factor. What conversion factor should I use? Okay. Here we started, and if we go back and look at when I added it, I wrote grams of aluminum. I didn't write a number next to it. But I said I wanted to convert between moles and grams. Okay. Why did I want to go to grams? What other information am I given? Grams of aluminum. So if I can do that conversion, those units cancel and everything's set. Can I do the conversion between moles of aluminum and grams of aluminum? Yes, that information is found on the periodic table. That is the molar mass for aluminum. Kind of makes sense?
Yeah. But the 2 moles of aluminum on the other side.
So we moved to the next one. We started with moles of hydrogen. We said, did we have moles of hydrogen?
Yes. It's in the equation.
It's in the equation. So I could write 3 moles of hydrogen, but that 3 is only if I react 2 moles of aluminum.
Right.
Am I told that I'm reacting 2 moles of aluminum? No. So that 3 is only valid if I write the 2 moles of aluminum underneath. If I don't write that underneath, that's now an invalid statement. Okay? That is only true because of the balanced equation. So when we are processing this, you have to be able to needle out where that information is found. Some of it must be memorized. Some of it is just given to you. Some of it is buried inside the periodic table or in the reaction equation that you may have to, number 1, create, and number 2, balance. Okay? Kind of makes sense? Okay, so let's take a minute to just stop talking about calculations. And Brandon, if you want, you can keep standing, but there's not going to be any calculations. I have no problems with you standing back there. Gas pressure. Okay? The pressure is the result of our particles hitting the container, and they are pushing outwards on the container. Okay? So we have a pressure whenever we have a gas. Okay? Do we have atmospheric pressure right now?
Yes.
What if we didn't have atmospheric pressure right now?
That's what I was going to ask.
You wouldn't be floating.
You'd be dead.
You'd be dead because there's now nothing holding you together, which means not a particularly pleasant experience. So let's avoid that. And let's have some atmospheric pressure. That pressure is going to push and keep us in and held together. Okay?
So we would explode?
Yes.
Is that what happens in space?
Yes.
Oh, sick.
It is pretty sick, as in disgusting. Right? No. Okay, let's just put this out to the audience just so everybody can hear this. Do we have videos of people exploding in space? That's generally not a valid experiment to go and throw some poor sap out into space to watch them explode.
Wait. So, you heard about that one astronaut engineer guy, right? Like, that when his suit leaked for a while, and they recorded what happened. It said it was like a weird putty sensation, like where his skin didn't necessarily, like as the pressure dropped, like his skin was actually being kind of sucked out. You heard about that, right? What happened?
I have not heard about that. I'm not sure I really want to hear about that. I'm not sure I really want to hear about that.
Well, yeah, no, it was like, because everyone thought like, okay, you just freeze and stuff, right? Or
Well, so there's a temperature issue too.
But it was like his skin was like coming detached from his body in a weird way.
Falling apart.
It was like, yeah, because it was like everything was
Because
just
nothing is holding us.
Right.
All the atoms are falling apart.
So it's not what you think, like we're not like this pocket tight.
Okay, so let's get back to it. Atmospheric pressure. Atmospheric pressure is the pressure of our atmosphere pushing against us. That's one of the reasons why we have liquids. It's one of the reasons why if you open up your container of water, we don't see the water come spraying out of it. Okay, why? Because atmosphere is pushing down on the water, keeping it contained. Okay? Without that pressure, everything just kind of sprays everywhere. That's not particularly fun. Okay? So, because this is an important phenomenon, okay, we observe it. And what somebody noted a long time ago was that when they noted the pressure at sea level, as opposed to, say, on Everest, that there was a significant difference in that pressure. Okay? Why would there be a significant difference? There's less air. There's less gas, which means less pressure. Because that now changes how we interact with the environment, it might be a good idea to come up with a system that can monitor that pressure so that we know, hey, this is really dumb and I should stop going up in altitude, or at least build an enclosed system that allows me to go up into space, as opposed to just flying up into space and be like, hey, check this out. Okay? Kind of a problem. So our atmospheric pressure is measured usually using something like a barometer. Okay? And within this, what we do is we take a tube and we fill that tube with a substance. Okay? We invert that tube in another larger container with more of that substance. Okay? What do substances do when at higher elevations? What does my pen do when at a higher elevation? It falls. Thank you. I should have dropped it closer to you.
Really?
It falls. So what is our liquid going to do? Fall. Okay. What is going to prevent that liquid from falling? What if instead of being an open container, I sealed it right here? Would the liquid fall?
No.
Why not?
Stay there.
The liquid can't fall because as it drops in the tube, what must it necessarily do?
Equalize pressure.
Rise on the outside. If I close that system, it's going to rise against a closed container, in which case
Push up.
it can't rise because it's closed off. What if it's an open system? What's it going to rise against? The atmospheric pressure, our air particles. So what we can do is look at the height of this substance in our tube. As we go to higher elevations, what happens to the pressure? It decreases, which means what does our liquid do? Goes down because there's less pressure pushing on the bottom of it.
Okay, that makes sense.
Our liquid will go down because what's keeping it up? It's this downward pressure here. Okay? When we go to higher elevation, what happens to the now red arrows of downward pressure? It gets smaller. If that gets smaller, what's preventing the liquid from coming down? In this specific case, yes. Okay. Nothing's preventing it, so it drops further. So we can monitor our pressure by saying the height of the substance in this tube. Okay. So we could come up with measurements of length, which is awesome because then we get which measurement of length? Millimeters, centimeters, inches. Okay. Why is that exciting by just listing those three things? They are all units of distance. And yeah, Jocelyn, you had the right idea there. That then means we have three different ways to measure that height, which means we have three different ways that we can convert between our units of pressure. Yay! Yes, chemistry is a large part of just converting stuff. Okay? What substance should we put in that container? What if I put in oxygen gas into that container? Would that work?
Yeah.
Why would that not work?
Because we wouldn't see it. I mean, it would work, but we wouldn't see it.
Okay. What happens to the oxygen gas in an open container?
It leaves.
It leaves. If I put oxygen gas in there, where does the oxygen gas go? It leaves. Is there anything to monitor? No. So a gas is a really bad idea. Okay. How about a liquid? Okay. We could put water in there. If I put water in that container, I could measure the height of the water. But if we opened up our container of water and left that out on the counter for 2 weeks, what happens to the water? It goes away. If it goes away, what happens to the height? It goes down. Is it going down because of pressure? No, it's going down because we've lost the measuring device. So we need a liquid that does not evaporate. Mercury is the classic substance for this. Okay. What we need to do is address the material property of mercury in comparison, say, to water. What that property is known as vapor pressure. It's the amount that your liquid goes into the gas state on its own. Okay? Which is kind of a weird statement. You say, well, but that doesn't ever happen. Well, we just proved an instance where it does. If we leave the water out on the counter, what happens to it over 2 weeks? It evaporates. Did it boil? No. Okay. I didn't provide enough heat to make it go into the gas phase, and yet it's still going into the gas phase. It's going into the gas phase because of this concept of vapor pressure. All liquids are in an equilibrium. I can't use that word. All liquids are in a balance between their liquid state and the gaseous state. Okay. Some liquids favor the liquid state. Some liquids favor the gaseous state. Water happens to be one of those materials that tends to favor the liquid state, but does have a significant amount going into the gas state. What is special about mercury for our thermometers?
It kind of stays all together.
It stays as a liquid always. Okay? Its vapor pressure is incredibly low. The amount of pressure that our mercury has in the gas state, so the amount of particles in the gas state, is low. Which means when I put it into this open system, the mercury doesn't disappear. It will always stay there, which then means the height of the mercury within that tube is only changing because of pressure, not because of some atmosphere or vapor pressure issue. Okay? Which is kind of a neat phenomenon. Yes? Could we theoretically boil mercury? Okay? If you provided enough heat, you can theoretically move any substance from a solid to a liquid to a gas. Okay? What is that point for mercury? I don't know. It's pretty hot. That's about all I know. You had a question too?
Ethanol was an interesting one because
Throw in
it
ethanol into the
evaporates,
mixture.
like, super fast, but at the same time the liquid just kind of stays there.
Ethanol evaporates faster than water. So if I had 2 containers of water and ethanol sitting out, I would expect the ethanol to evaporate faster than the water. Why does it evaporate faster? Careful. If it has a lower vapor pressure, we're saying there's less particles in the gas phase. If it's evaporating faster, there's more particles in the gas phase, which means higher vapor pressure.
So is it higher or lower?
It's higher.
Okay. So why do we use that as like thermometers and stuff?
What did we want for our thermometers? A high vapor pressure or a low vapor pressure? We wanted a low one. We want it to never dissipate. We can use different alcohols. So you really don't, because that's a nomenclature issue that you don't want to open up.
Okay.
Yeah. Okay. What happens to our vapor pressure as we increase temperature? Well, it says here it increases. Why would it increase? They're more active, okay. What happens to a liquid when you heat it up? It turns into a gas. What is vapor pressure?
Gas.
Turning into a gas. What's going to happen when you heat up a liquid? If it's going to become a gas faster, your vapor pressure is increasing. Okay? Kind of makes sense?
Yes.
Okay. What about dissolving a gas into a liquid? Okay, we actually already talked about this. I now want to get my gas dissolved into the liquid. How can I do that? Why remove the temperature? Okay. My gas is freely moving. If I want it to be trapped in the liquid state, I'm trying to make the gas go to a liquid. How do I do that with temperature? I cool it. Okay. So a lower temperature is going to get the gas into the liquid state. Okay. We've now added a new system or a new kind of variable that we could now evaluate as well. Okay. What could we do to the pressure? I'm trying to get this gas that's free flowing, moving everywhere, and now I'm saying be here. I need to increase the pressure. I'm saying you can freely move wherever you want. Now you cannot move wherever you want. You must be here. The only way to do that is to grab each and every single one of those particles and jam them down into one spot. Okay, so if we want to increase the solubility of our gas, okay, we're trying to dissolve more gas, we want to increase the pressure, and we want to decrease the temperature. Okay? So here's the fun part that we started to allude to, the units of pressure. Okay? The standard unit that is typically used is atmospheres. Why do we use atmospheres? What is standard pressure? 1 atmosphere. Why do we use atmospheres? It's an easy number to work with. Okay? So that's the system we use, which is kind of bizarre because we talked about pressure being measured by the height of a mercury system. Okay? Well, is atmospheres a measure of height? No, so we invented a new unit, okay, and could relate that back to the height. Okay? So if we go through and look at a variety of different ways to define pressure, 1 atmosphere is our atmospheric pressure, which is equal to 29.9 inches of mercury.
So it's already converted for it.
It's already set up as a conversion factor, okay, which is also equal to 76 centimeters of mercury, 760 millimeters of mercury, 760 torr. What the? Torr?
Exactly.
14.7 psi. What the heck's a psi? Pounds per square inch. Thank you, America. 101 kilopascal. Wait, Pascal? What is that doing? What are all these different units coming from? Pressure is such kind of large concept that had been defined in multiple locations around the globe. Each of those people then defined a unit system to measure that pressure with. Then we globalized and people started communicating with each other. Okay? One scientist says, this is how I monitor pressure. And the other scientist will says, this is how I monitor pressure. Okay? Are either of them wrong? No. What should they have done? Agreed to a single unit. What did they do instead?
I'm right, you're wrong.
I'm right, you're wrong, which then means whoever teaches whichever unit uses whichever unit they want, which then means you get to convert them all.
Wow.
You're welcome.
Can't we just fix it?
Can't we all just get along? Yeah, that we've already proven that doesn't happen.
So what's the universal?
Okay. So atmosphere tends to be the standard within science, but it depends again on which system you're looking at. Okay. So for you guys, do you really need to know all of those conversion factors? No.
No, just to reference.
At worst case, I would give you those conversion factors on the exam. Okay. At best case, I don't even ask those questions because I think it's a waste of freaking time. And I recorded that too. Man, I'm on a roll today. Okay. Hey. Just gonna move over here. If you move into 151, you're going to be responsible for all of those conversions. Within 130, you don't need to stress about all of those conversions. I provided some practice in the homework, but that's all I expect you to do. So now let's move to the fun part. What are things that affect pressure? Temperature. So if I look at pressure and temperature, how are they related?
The more temperature you have, the higher the pressure.
If I increase the temperature, what happens? The pressure goes up because?
Because the temperature means faster speed of molecule.
All the particles move faster, which then means they hit the walls harder, and we get more pressure. Okay? So what we can do is say that those are proportional to each other. That's what that little, it's not really an alpha. It's like a half infinity symbol. They are directly proportional. When I increase one, the other one also increases with it. Okay, so that is a variable that affects pressure. What else affects pressure? Okay, the volume. How are those related?
Well, depending on.
They're inversely related. What do you mean? If I increase pressure, does the volume not also increase?
Correct. Well, depends. If the volume is like expandable, I guess.
What happens when we change our volume? Let's focus there.
We allow more room for.
If we increase the volume,
to lower the pressure.
the pressure goes down because now our gas particle, to reach the wall to exert a pressure, has to travel further. There's less impacts at the wall because there's a larger wall space.
So you have that more gas.
So they are inversely related. As I increase volume, my pressure goes down. How can I relate that mathematically through that same kind of proportionality idea? It's a harder question.
What's weird though is
What happens if I increase the volume? What must happen to the pressure? It has to go down. So they are inversely related. Where do I see inverses? 1 over V. Okay? That is now our relationship. There is one more variable that affects our pressure. The number of particles. Okay? Or our moles. What was that?
really playing like
He's playing footsie or something? Okay. What happens when we increase the moles? So they are directly proportional. You made an sound as in you
because like
didn't agree or agree? Okay. Remember, pressure is measured by the amount of impacts on the side of our container. If we put more particles in there, more opportunities hit the side of the container. So we have a direct relationship there. Okay. Remember how we've talked about how scientists are lazy? Moles is too many letters, believe it or not. Big M, though, is molarity. Little m is meters. Fair enough. I didn't even consider that one. I was going to say mass, but yeah. So little m is a big mess. So what can I use for a unit there?
A different symbol altogether. It's I don't understand.
N. That's what it is. Okay. What we can do now is take all of those relationships and combine them into one massive equation. Okay. That one massive equation allows me to then solve for pressure, temperature, moles, and volume. Without that equation, if I know the moles, can I solve for the pressure? I just know that it would go up or down, but I don't know anything else. So I want to actually be able to solve for these things. Okay? These relationships, of course, get attached to somebody's name. I don't care about the name. All I care about is that you recognize that relationship. Okay? And so your textbook mentions a bunch of these. What we can bring this all together to do is we can end up with this fun little equation. The pressure times our volume divided by the moles times our temperature. And what we found is that when we do that, regardless of what our pressure, volume, moles, and temperature are, when we run that calculation, we always get the exact same answer. It never changes. We have a constant. That constant is 0.0821 atmospheres, because atmospheres is a measure of pressure, liters, volume, moles, we came up with some stupid symbol, and K, Kelvin, our temperature. Okay. We now have a way to relate all of those seemingly independent variables and put it into an equation where we can now solve. Okay? If I want to know the temperature for an individual system, what do I need to know? What information must be given? If I want to know the temperature for an individual system, what do I need to know? For an individual gas system. I'm looking at a sample of gas. What do I need to know to determine the temperature? Solve for temperature, right? PV. Okay. I need to know the pressure, the volume, the moles. Do I also need to know R? It's a constant, so yes, I need to know it. Theoretically, we could memorize it. Okay. I used to have it memorized and admittedly have completely forgotten it. I never remember how many zeros to include. Okay. Will it be on the exam? The next exam, yes. The final, unfortunately, no. The way the final is designed, you are given no information. This is why you should review the exam information that I give you online, because I tell you what stuff you should memorize. Yes, Eddie?
Isn't the constant change with the different, like if it was toward instead of atmosphere?
There's an interesting question. So let's rephrase Eddie's question or repeat it. Shouldn't the constant change? No, it's constant. He did not stop the question there. Should the constant change if I have a different unit for pressure? Yes, because that means I'd have to fold a conversion factor into that to get my pressure unit in R to match out the pressure unit of my pressure. Okay?
So are we going to have to memorize that?
So the only reason you would need to know those other R values is if you were using a different pressure unit. Okay? But what did we say you had to do? Whoa, black screen, that's not fun. Okay. What did we say you had to do with all those pressure conversions? I said, what did I say? I said don't memorize it, don't worry about it, because you're not going to have to do it. So the question that you're asking, does the R change when you use a different pressure? Yes, that numerical value does change. Should you have to memorize that one also? No. Could you convert it from knowing those or using those conversion factors? Absolutely. Okay. Why do we stick with this one, the 0.0821, most commonly? What is our standard unit for volume? Liters, standard unit for amount. Moles, our standard unit for temperature. Kelvins, our standard unit for pressure. Atmospheres. So we tend to use mainly only this one. Okay? It can be made more difficult by changing whatever that pressure unit is. And for those of you that have to deal with that, I apologize in advance. Okay? Where else can this be useful? We just did that. Okay. We know we have a constant here. If I have a gas under conditions A, what is the R going to be? 0.0821. If I have a gas at conditions A, I don't care what the pressure is, the volume, the moles, the temperature. The R value will be 0.0821. What if I move to a gas at conditions B? What will the R value be? The exact same thing. Why is that now helpful? What can I do with these? What's that? No? Set them equal to each other. Okay? I can go through and now build a relationship between these two systems. Pressure A, volume A, moles A, TA equals pressure B, volume B, NB, TB. Yes, go ahead.
So the pressure and moles are always the same?
Careful. Is the pressure always the same? No, the constant is always the same. If I change the pressure, what else is going to happen? The other things will change, not the constant. So if I double the volume of a container, what happens to the pressure? Okay. Let's look at our equation. Okay. Are the moles different? No. So what does Na equal? NB. If I have 1 over 2 equals x over 2, what is x? 1, because I can cancel the 2's. What can I do to the moles? Okay. Is the temperature changed? What can I do to the temperature? Okay. Now we've got to get a little bit careful here. The volume of the container is doubled. So volume B equals what? Twice volume A. What can I do? What are we solving for?
Pressure. So you have pressure. You doubling volume.
We can substitute in. What happens? PA VA equals PB 2 times VA. What happens with the VAs?
Cancel out.
They cancel. And what do I see? Pressure A equals twice pressure B. What happened to the pressure in B? What happened to the pressure in B?
Oh, you're saying like highly.
It halved. I didn't say you were wrong. What are we solving for if we're looking for pressure B? Pressure B. Have we solved for pressure B yet? 2 PB is just PB? Or not 2B? Your turn. What is pressure B? Pressure B is 1/2 pressure A. That is the equation we need to solve for. We want PB isolated. PB was not isolated before. I solved for pressure A. I know pressure A is twice that of pressure B. Okay? So we've got a neat way to come up with those relationships. We can see how our pressures, volumes, moles, and temperatures will change. And in that problem, did I tell you what the volume was?
No.
Did I tell you what the pressure was?
No.
Did I tell you what the moles were?
Can you tell us anything?
I didn't tell you anything except double it. And with the power of that expression, R equals PV over NT, I can tell you what happened to the pressure. I may not know its exact value, but I know how it changed in the course of the reaction. That is a powerful piece of information. What was that? We can talk about what you missed after class. Okay. Sure, why not? How many moles of neon gas occupy 2.34 liters at STP? Okay, and this is going to be one where you can do this fast and you can also do it long. And I'm going to show you long in a second. What are we looking at? Moles, how many moles of neon gas? So I may say moles of neon gas first, but that's what I want. N2? N2 is nitrogen, not neon. What about neon? What is the formula for neon? It's just Ne, it's not Ne2 because it's not a diatomic gas. Have no fear of ice cold beer. None of those letters are neon. The no is our nitrogen.
So because it's a...
What did we start with? 2.34 liters. Can I convert moles to liters? How do I do that?
22 or 1. Yeah, there you go.
I keep doing that. 22.4 liters is 1 mole.
Correct.
We did that. Okay. What's the long way to solve this? I know you love to do the long way.
Finding out the moles of... There you go.
PV equals nRT, right? All I did was rearrange that. That's the standard format for the ideal gas law, not what we saw before, because this way it's all in the numerator, nice and easy. My old chem teacher used to claimed that she got a license plate that said PV space nRT, and then drew in an equal sign, and she got a ticket because she altered her license plate. I don't believe it, but that's what she claimed. It's also referred to very commonly as pivnert. You may hear a reference to that, pivnert. That's what we're referencing. So if that was our equation, how do we solve for moles? What of those symbols was moles? N. N is equal to? Fair enough, I'll write that. I asked for it.
Equals atomic mass.
PV over RT.
Oh, because you're trying
In the equation, or in the question asked, what were we given? We were given the volume. What is P? Oh, whoa. I don't know why I drew a T there, or a 2. Over RT. What did we say P was? Why did you say 1? We're at standard temperature, so it's 1 ATM. What was R?
0.8008.
I sure hope that wasn't sarcasm. Good. What is our temperature? Our standard temperature. Ooh. 0 degrees Celsius, but I need Kelvin, so it is 273 Kelvin. That is standard temperature. The Kelvin units cancel. The atmosphere units cancel. What do I get as a unit out of that? I get actually moles over liters. We're dividing by a fraction. Your fraction flips. What was our conversion factor? What was our units? Moles over liters. Interesting. By doing the ideal gas law, we got moles over liters. Any guesses what 0.0821 times 273, 1 divided by that number is? 22.4.
Is that what you meant by they always do the same thing?
Whoa. PV equals nRT gets you the relationship between 1 mole and liters. That relationship is always valid. That is what PV equals nRT sets you up with. Because you will always know the temperature, you will always know the pressure. That is why PV equals nRT is important, and why the 1 mole is 22.4 liters is a load of complete and utter nonsense, because it is only valid at standard temperature and pressure, and only valid when it's a gas.
So,
Okay.
I guess
If we're in a gas, PV equals nRT, we don't have to worry about standard temperature and pressure. Our equation solves it. Right? If, for the sake of this class, ultimately all you really need to get out of this, unfortunately, 1 mole equals 22.4 liters.
but like,
I can't possibly provide a lecture on that and just accept it. I've got to show you the background. That's where it's coming from. With that, I have to be done.